Hello, so welcome. This is kind of a extra video on my series that I'll be doing to explore the deep wonders of the universe and reality and really probe it, being inspired by a kind of Luciferian spirit, if you will. And this video will be talking about essentially what is an atom? An age-old question, what is the universe fundamentally made of? And I'll be talking very briefly about the twists and turns. This will be fairly kind of like very light. If you see my other videos, I tend not to throw in too many equations. It's mainly kind of going to be discussion based, but really the search for what is an atom demonstrates the wonderful determinism of the human spirit and willingness to do the seemingly impossible to determine what the universe is made of when we're dealing with scales we can't even physically observe, and which actually arguably might not even be physical in and of themselves, which is something I'll come on to talking about in a moment. So I really hope you enjoy this video, and let's dive into the discussion of this wonderful journey towards discovery. So to begin with, the idea of atoms, though it's kind of attributed to more modern times, actually dates back kind of much further. I mean, the idea of kind of the universe being made of fundamental particles is something which probably goes back remarkably far, far farther than we can actually tell. But most certainly it was popularised, a fervent believer of this in ancient Greece was Diophantus. And Diophantus really popularised the idea of kind of, well, if not popularised, really drove the movement forward based on the idea of the universe's material as being made of fundamental particles. And indeed, the name atom actually comes from the ancient Greek word atomos, which means invisible, because the postulate was that the universe was made of these particles, but we can't actually see these particles because these particles are so incredibly small. They didn't really know the size of them, and this kind of is a nice model to have. And it was, in a way, going down the right tracks. There are problems with it, though, because if you assume that everything in the universe is made of, a particle, unless you've got a very large number of those kinds of particles, if it's just fundamentally an atom, well, if an atom is fundamentally a single particle, it's very hard to explain the variety of behaviours and materials, like heat capacity, ductility, radioactivity, and all of that which we see today, and which they would have seen back then, because there's only so many ways you can arrange these things and have clusters of them. However, by having different arrangements, you could have different physical properties. So this model isn't completely ludicrous, but it's fairly incomplete. However, kind of structure does have an effect on things. For instance, the structure of water molecules has an effect upon the density of water, and actually of the breaking of the tetrahedral structure of water molecules seen in kind of a solid, actually at low temperatures causes the liquid water to actually have a higher density than it does when the liquid water was solid, which is why ice floats on top of water. So the structure of kind of molecules and possibly these atoms could have a massive effect, but to explain the full variety we need something a bit more substantial. So is that the wrong answer? Well, what kind of Thomson comes along, and Thomson managed to show that atoms, Thomson much later, we're talking, much later in history, so era of kind of classical physics. But Thomson demonstrated that atoms actually, contain negatively charged particles called electrons. So in his model, you essentially have these electrons which go around in this positive goo, and it has to be positive goo because the overall atoms are neutral, because most matter doesn't have an electric charge. If I touch most matter, I don't usually get a massive electric shock, and therefore, matter kind of must generally be neutral. And so if the electrons are charged, and you also showed that they were negatively charged, then the kind of goo they're orbiting in must have positive charge, so that the charges cancel out and the overall atom is neutral. And this is reasonably good to an extent until it was found by Rutherford in the Rutherford scattering experiment that actually atoms are not of uniform density, which the screen model would kind of roughly suggest, because an electron has such small mass, its added density to the goo is virtually negligible, so the screen model would predict uniform density. So maybe the goo model was actually wrong, and a right answer would be the Rutherford kind of model, where as Rutherford showed, the atom has a very dense region, and much more than this you can show by kind of repulsion that this region is positively charged, not neutral. So in his model, you have electrons orbiting around this very dense central thing in the atom, and we call this dense central thing the nucleus. So in the Rutherford model, we essentially have electrons going around kind of planetary-like orbits around this nucleus, where the electrons are like planets, and the nucleus is essentially like the sun. So you get a nice comparison to the model of the solar system. However, even this has its problems. So is the answer wrong again? Well, the problem really with this model is, the electrons can essentially orbit at any radii they like, just as planets can orbit the sun at any radius. I mean, they orbit now at set radii, but if you put a planet in orbit, it could start orbiting the sun at any radius. If you could just drop a planet in the solar system. And this essentially means that electrons should be able to orbit at any radius, and therefore should be able to be at any energy. And we don't actually see this. We see electrons by the emission spectrum of atoms like discrete energies. And another problem is the Rutherford model is inherently unstable, because classical electrodynamics says the electron should emit electromagnetic radiation as it kind of accelerates, because it's still orbiting around the atom, so it's changing direction and therefore accelerating. And therefore the electron should emit electromagnetic radiation, lose energy, and kind of collapse into the nucleus. So atoms should be incredibly unstable, but thankfully we kind of see in daily life atoms are very stable. The universe doesn't turn into a burst of gamma rays. We're not in some kind of like Ultra Hulk movie where the universe has just decided to zap another universe with gamma rays and turn its life forms into kind of Hulk. So something is very, very wrong with the Rutherford model, and we need to impose a really bizarre thing, which is that electrons have discrete energy levels and therefore can only orbit the nucleus at specific radii. So we have the Bohr model now. Now the Bohr model of the atom actually took inspiration from suggestions by Di Broglie, and his suggestion was essentially, well, the electron though it seems to be a particle, might have wave-like properties. I won't go into where this comes from. I know it sounds kind of really bizarre to say a particle might have wave-like properties, but actually following on from Einstein's work in the photoelectric effect, it actually made reasonable sense that this might be the case. And it turns out that Bohr's model of the atom is equivalent to essentially saying the electrons from standing waves around the nucleus. And standing waves are the kind of waves you see on, forming on a guitar string. They're very stable. And because, the electrons form standing waves, they, you can only fit a certain number of wavelengths around a particular orbit. And so this restriction of standing waves actually means that the electrons have to orbit at specific radii and can't pick any radii they like. So we have this quantization of energy in the Bohr atom from considering the wave particle nature of electrons, which is a really ludicrous thing, but maybe we're getting somewhere. We finally got the thing that explains but to a very good degree, the hydrogen emission spectrum. So if you heat up hydrogen atoms and they excite and start to emit light, the Bohr model does a really good job at predicting what wavelengths you will and will not observe. So maybe we're actually finally here, but no, actually we're kind of not really there. And the reason is because the Bohr model works great for hydrogen. It completely fails when we're dealing with atoms with more than one electron, such as helium or other atoms. So essentially it works for hydrogen, the Bohr model, not really for anything else. And the problem, one of the other problems is the Bohr model violates Heisenberg's uncertainty principle, so it keeps some of the wave-like nature of particles, but kind of ignores the fine detail, because the Heisenberg uncertainty principle essentially comes from considering in detail the wave-like nature of electrons and the consequences of thinking about particles in terms of waves and their wave-like natures. And so we need a new formulation, and that was kind of developed by Schrödinger. And you have the Schrödinger model of the atom, but in this model it's even more bizarre than the Bohr model, because in this model the electrons aren't actually physical things really at all. At least we don't really, in the mathematics, consider them as being physical. That's not saying they're inherently not, but we seem best to be able to describe them in terms of a wave function, and this wave function gives the probability distribution, which gives the probability of finding an electron at any point in space when we actually measure where the electron is. But in general, the electron is just this fuzzy cloud of probability, so the electron isn't even physical. And it gets even worse when you think about well, if the electrons are described by wave functions are particles within the nucleus, it actually turns out the nucleus is made of individual particles in and of itself. Is this nucleus that Rutherford discovered, can we talk about a wave function for that? And if we can, which it turns out we can, is the nucleus just a fuzzy thing of probability? So is anything in the universe actually physical? And it's a really startling, really incredible thing. And the answer is we really don't know. And there's a huge amount of debate around this and on developing quantum mechanics and trying to make something more reasonable. But I hope this has shown you, the wonderful jiggery-jaggery search, the bumps along the road, the surprises, and giving an introduction to what the atom is and how our thoughts on it have evolved with time. I really hope you've enjoyed this video. Wishing you all the best.